Okay. Hello students, my name is Sumit Sagar Hota. I'm a PMRA PhD student at IIT Palakkad. Today we will discuss lecture 55 to lecture 60 by Professor Sagar, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion. This is the week 12 of the live discussion section. In this section we will see some of the MCQs, and at the end I will solve some of the maybe 2 or 3 problems. Okay, so start the section. Okay, so first question is, how many burners are placed in a can annular combustor in a gas turbine? Okay, so the answer is actually it's not that much specific. Okay, so anything 1, 3 or 5, anything can be option. So the answer is answer D. So multiple or single burners are evenly placed in a can annular combustor. So here in this statement the most important word is this one, evenly spaced, and the next important will be multiple or single. Okay, so maybe one more question can be asked, that in can annular combustor the whatever the combustors are there, is this evenly spaced or it's not unevenly spaced? So that type of question can be asked. Okay, so the silo combustor are mounted internal to the gas turbine body. Okay, so this is actually kind of theoretical questions. If you know it, then only you can answer this question. Actually this is a false statement. Silo combustor mounted external to gas turbine body. Okay, so the next one, the axial flow turbines are used in dash. Okay. The axial flow turbines are used in industrial gas turbines. Okay, what completes a stage in expansion? Okay, so what completes a stage in turbine expansion? The answer is C, the stationary blades row followed by the moving blades row. Okay, see. Okay, then what does TRIT in a gas turbine stands for? Okay, it's a turbine rotor inlet temperature. Okay, and what is TIT? It's a top turbine inlet temperature. Okay, so 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 the answer of this question is A. So when at ideal condition, gas turbine engines use more fuel when compared to a reciprocating engine. Okay. So ideal condition means obviously in general in ideal condition there is less fuel consumptions are there, but when there is a comparison between a gas turbine and a reciprocating engine, because a reciprocating engine having more rotating parts or reciprocating parts, so that's the reason it requires more fuel as compared to a gas turbine engine, and gas turbine engines are, that's the reason, lightweight also. Okay, because less moving parts. Okay, that's the reason it requires less fuel in idling condition. But so the answer is A. In ideal condition, the gas turbine engine use more fuel. Okay, so compared to reciprocating engine. But the problem is here actually it's not deals with the fuel what is inside the engine. Rather, it requires it they are talking about because they more fuel. Okay, so yes, when there is a fuel they are telling, then obviously gas turbine is less efficient. Efficiency came into existence. So efficiency, because of efficiency only this gas turbine requires more fuel and reciprocating engine requires more fuel, less fuel. So ideal condition, this statement is only written for confusing. If in place of this question there will be slight modification in the question. Let it be, when an ideal condition the gas turbine engine uses more engine oil when compared to a reciprocating engine. If this is the statement, then this statement will be what? False. Okay, because inside the engine it require more fuel for a reciprocating engine. Okay, so if more fuel they are telling, that means obviously because it depends on the efficiency and ideal condition in general they are in general ideal condition both requires less fuels. Okay, but when there is a comparison, obviously the efficiency came into existence and the gas turbine requires more fuel. Okay, because it's less efficient. In gas turbine, compressor raises the pressure of air by dash times. Especially they are telling that is the compression ratio for a gas turbine compressor. Okay, so it's actually very high. This is actually 30 times. This is the maximum value. It should be noted that it is the maximum value. Sometimes it can go this much, or otherwise 20, 15, 20, or sometimes only 30 it will go. Okay. In gas turbines, turbine is used to convert gas. Okay. Turbine is always used to convert the kinetic energy to rotational energy. Okay, the radial equilibrium theory assumes that that flow is in the equilibrium before and after the fluid entering the blade. It's actually a true statement. Based on type of flow arrangements, gas turbines are classified into dash. Okay, so based on the type of flow arrangement, gas turbines are defined in two types. One is axial flow, one is radial flow. But in the option only axial flow is there, so you can choose answer D. Okay, so next will be dash is developed when working fluid is passed through a blade passage. Okay. Blade passage always reduces the heat loss inside the engine, not outside. That means it's a inside, that means internal. It reduces the heat loss, so it reduces the heat, that means it's a heat loss, so it's a internal heat loss. Okay. So why it will reduce? Due to the what? The heat is lost due to the friction, okay, between the blades material and the fluid. So then kinetic energy of working fluid is dash kinetic energy of the case losses flow. Okay. Okay, so whatever the kinetic energy of working fluid is always greater than that of the kinetic energy of the case lossless flow. Okay. Uh, Okay, that means they're telling that is due to the case whatever the law kinetic energy loss is there, is it higher or lower than the whatever the loss it's there in the working fluid. I already told the kinetic energy due to the kinetic energy of the working fluid is due to the whatever the loss is there, it's due to the friction. Okay, but here in the case already some blades law, it's actually it's a little more complicated than that of the whatever the blade when it passed through the blade passage. So that's the reason why the kinetic energy always higher in case of the working fluid as compared to any kind of loss in the case whatever this case lossless flow. Okay. Okay. Ratio of the actual velocity to velocity case lossless flow is called what? Okay, it's called velocity coefficient. It's an important term. Okay. So any kind of coefficient will be there, means it will be the higher one will be always on the numerator and the lower one will be always in the denominator. If you see the velocity in the actual or the due to the only casing due to the only blade passage or due to the only working fluid, it is higher. So that's the reason this is always high. Okay, and we cannot directly write down because it also depends on the working condition. Okay, in general B actual is always greater than B lossless. Okay, but it depends on the type of working condition, it can be also varied. Okay, so that's the idea, because it can be one also, because it can be both will be equal. Okay, that's the difference between the actual enthalpy of working fluid to the case enthalpy of isentropy flow is called as what? Okay, so this is actually obviously actual minus isentropy. Isentropy is the ideal condition, actual is the whatever the actually is going on for a irreversible process. Okay, so that means there will be some losses for the what actual processes. So that the difference will be obviously the losses. Okay, because in isentropy flow there is no loss. Okay, so the answer is C. Next, the losses occur due to the enthalpy changes is caused due to dash. I told already, all the losses caused by the what? Due to friction. Okay, and due to which there will be a temperature change, and due to the temperature change there will be a what? Enthalpy change. The velocity coefficient is applicable for dash. Okay, so it doesn't depends on any kind of flow passage, actually velocity coefficient, because it depends on two factors. One is your B I already told B actual, and whatever there is a loss. Okay, actual to the lossless. So that's the reason why it doesn't depends on the passage, rather it depends on the in which type of pass, means what is the how much percentage of blockages are there, not on the flow, what type of flow passage. Okay, so that's the thing. If in the question it's written parallel flow passage with 50% blockage, and one will be same parallel flow passage with 50% 25% blockage. So those cases, these things will be considered. Okay, the which one will be higher and which one will be lower. Okay, so it depends on that formula whatever I told before. Okay, higher blockage leads to lesser velocity. That means your V actual will be going to be your V actual will be higher, and your V whatever loss, there will be too much loss. Higher blockage leads to more loss. Okay, that means the whatever the coefficient value will be what? Higher. Okay, because denominator is decreasing. If you see in this formula, so if your there will be more blockage leads to more whatever the velocity, will decrease. So that means denominator will decrease due to higher blockage. If the denominator will be decreased, actual velocity always constant for a particular blockage. Okay, so that's the reason why your velocity coefficient will what? Going to increase. That means it can be changed depending on the blockage, not on the type of passage. So it is applicable for all type of passage. The velocity coefficient can be applied for dash flow passage. That this thing I already told, it does not depends on the flow passage. Okay, so that means it can be applicable for any kind of flow passage. Okay, so answer will be none of these. And the most of the cases you didn't choose the option none of the mentioned when you are not sure. That's the reason why this kind of question can be set, and these are tricky questions. The velocity coefficient can be applied for dash blade passage. Okay, same flow passage, blade passage, these are some of the what do you call synonyms. Okay, so that's this way they can actually confuse. One question they you will flow passage, one question they will give you blade passage. So in one option you will tell it depends, then you tell no it does not depend, then it's wrong. Okay. Okay. The blade profile losses for diffuser blade depends on dash blade whatever this profile losses, blade profile losses, that it's actually name suggests everything. Okay, velocity profile losses, profile, that means there is some change in profile due to which there is a loss. Okay, diffuser blade nozzle, whatever the nozzle if there is blade. Okay, most nozzle there is no blades are there, but if there is blades, okay, that's a different thing. So whatever the diffuser blade, that does not matter. The major thing is the blade profile losses. Okay, that's the important term in the question. So blade profile loss means there is a change in profile due to which what the velocity will be going to change. If there is a velocity change, that means there will be a kinetic energy takes into importance. Okay, depends on the kinetic energy. Okay. The blade profile losses are dash losses of the stage at a turbo machine. These are very small losses because the frictional losses always considered as the small losses. Okay, not the greater or equal or something like that. It's always a small loss. Okay, frictional losses. A turbine having alternate blades and nozzles is called as what? This is a very simple question. Okay, it's actually a definition of your impulse turbine. Okay, a turbine having alternate blades with blades as well as nozzles is called as impulse turbine. Okay. The multi-stage arrangement of turbine is called as dash. Multi-stage. In this question, the important word is multi-stage. Multi-staging is also known as compounding. Okay. So directly the answer is C. Because in this type of question, in the question itself, the answer is given. Okay, so it's very easy to answer. So more specifically, if I will tell what is compounding, what exactly going on in compounding, there is always a pressure loss, decrease in pressure loss and velocity loss. Okay. Okay. So this is the very good advantage of a compounding. Due to compounding, your efficiency will going to increase at a very low speed. Okay, because it reduces the loss. Okay, at the low speed, especially frictional losses. In pressure component turbine, moving nozzles are followed by turbine blades. True or false? It's actually a false statement. So next will be, in pressure component turbine, flow passage is from dash. Okay, this from fixed nozzle to the moving blades. So in pressure compounded turbine, flow passage is from dash. Dash is the fixed nozzle to the moving blade. Okay. Okay, the next we start the problems. Okay. A radial flow turbine of the following geometry is tested under design condition with a pressure ratio of P01 P01 to P3 F2 at our inlet temperature of 1000 Kelvin. The work output after the allowance has been made for the mechanical losses is 45.9 kilowatt. When the rotational speed is 1000 revolution per second and the gas mass flow is 0.322 kg per second, the rotor inlet tip diameter is 12.7 centimeter, rotor exit tip diameter is 7.85 centimeter, hop tip ratio at exit is 0.3, nozzle efflux angle phi 2 is 70 degree, rotor vane outlet angle beta 3 is 40 degree. Separate test on the volute or nozzle combination showed the nozzle loss coefficient lambda n to be 0.07. The turbine isentropic efficiency and rotor loss coefficient lambda r to be evaluated from the results. Okay. So first of all, from this question, one pressure ratio P01 to P3 there. This is actually a hint to use one specific formula. Okay. Okay. Okay, the formula is T01 minus T3 dash is equal to T0 1 minus 1 by P01 by P3 to the power gamma minus 1 by gamma. Okay, that's equal to, substitute the values, 1 minus 1 by 2 to the power 1 by 4, 159.1 Kelvin. Okay, so what I want then we'll find out the work W. Okay, W dot equal to m dot Cp delta T T01 minus T03. Okay, so from here we can find out T01 minus T03. Substitute the values, (124.2 Kelvin) efficiency, 124.2 divided by 159.1, 0.781, and this is your answer. Okay, next we need to find out what R3 by R2. R3 by R2 is equal to 0.3 7.85 plus 7.85 divided by 2 into 12.7. Okay, this value comes out to be 0.402. So next we need to substitute all these values. Efficiency, what is the formula for thermal efficiency? 0.781 is equal to 1 plus 1 by 2, 0.402 square plus cot square 40 plus lambda r cosec square 40. Okay, it's into, okay, plus 0.07 into cos square 70 inverse. Okay, lambda r is your 0.64. So now next come to the next question. Okay, so a single stage gas turbine operates at its designed condition with an axial absolute flow at entry and exit from the stage. The absolute flow angle at the nozzle exit is 70 degree. At the stage entry, the total pressure and temperature are 311 kilopascal and 850 degrees Celsius respectively. The exit static pressure is 100 kilopascal. The total to static efficiency is 0.87 and mean blade speed is 500 meter per second. Then assuming the constant axial velocity through the stage, determine the specific work done, Mach number leaving the nozzle, axial velocity, total efficiency, and stage reaction. Okay. Okay, so let's start this question. This is the TH diagram for this above question. Okay, so Okay, so total to static efficiency a bit. See, this is the a bit, the specific. Okay, so first of all we need to find out the specific work done. Okay, for that we will take first the total to specific efficiency. Work done, total work done divided by Cp T01 1 minus P3 by P01 to the power gamma minus 1 by gamma. Okay, so the specific work done will be 0.87 into 1148 into substitute just the values 1123 into 1 minus 1 by 3.11 to the power 0.248. Okay, so yeah, next your work done will be what? If you solve it, you will get 276 kilojoule per kg. Okay, this is your answer. Okay, so next we need to find out what we need to find out the Mach number leaving the nozzle. Okay, or the Mach number at the nozzle exit. Okay, so at nozzle exit, okay, m2 is equal to c2 by square root of gamma r d2. Okay, cw3 0, cw2 wt by u, and what is wt? U into cw2. Okay, so what is cw2 now? Convert it into joule per kg, multiply 10,000 10 to the power 3 divided by u is your 500, so the unit is 552 meter per second. This is cw2. Okay, Next we find out C2 is equal to CW2 divided by sin alpha 2 equal to 588 meter per second. What is T2? T2 is equal to T01 minus half C2 square divided by Cp. Solve it, get 973 Kelvin. Then substitute out everything in M2 and find out M2. M2 is equal to 588 divided by square root of 1.33 284 into 973. Okay, the M2 will be 0.97 then. Okay, now the axial velocity. CA is equal to C2 cos alpha 2 is equal to 200 meter per second. The next will be total efficiency so what is total to total efficiency? Oh. So next substitute the values. 1.1 by 0.87 minus 200 square divided by 2 into 276 into 10 to the power 3. So the total efficiency is 0.93. This is your answer. What is the degree of reaction? The degree of reaction let represent by Rx 1 minus 1 by 2 Ca by U velocity triangle tan beta 3 is equal to U by Ca and tan beta 2 is equal to tan alpha 2 minus okay. So next Rx is equal to 1 minus, okay, just rearrange the things, okay, 1 minus 1 by 2 Ca by U tan alpha by 2, so tan alpha 2, okay. Substitute all these values and find out Rx. 1 minus 200 into 0.2745 divided by 1000, okay. The degree of reaction is 0.451. Okay. So this is the last question of the section, okay, especially last problem of the section. So the question is, the combustion gases enter the first stage of a gas turbine at a stagnant temperature and pressure of stagnation temperature and pressure of 1200 Kelvin and 4 bar. The rotor blade tip diameter is 0.75 meter. The blade height is 0.12 meter, and the shaft speed is 10,500 rpm. At the mean radius, the stage operates with a reaction of 50%. Okay, a flow coefficient of 0.7 and a stage loading coefficient of 2.5. Determine the radiative and absolute flow angles for the stage, velocity at the nozzle exit, static temperature and pressure at the nozzle exit. Assuming a nozzle efficiency of 0.96 and the mass flow. Okay, so these are the things. Okay, so let's solve it. Okay, so first we need to find out the what. Okay, so first we need to find out the relative and absolute flow angles for stage. Okay, so for that we need to do the stage loading. Okay, okay, so here a psi equal to delta H naught divided by U square is equal to BW3 plus BW2 divided by U. Okay, is equal to CA by U into tan beta 3 plus tan beta 2. Okay, so yeah, so next what is Rx? Rx is equal to CA by U tan beta 3 minus tan beta 2 divided by 2. Okay, so now we need to find out this tan beta 3 and tan beta 2. Okay, because it's beta 3 beta 2. Okay, especially we need. Okay, and that L, and we know for a reaction 50% reaction, alpha 2 be equal to beta 3, alpha 3 equal to beta 2. Okay, so this alpha 2, alpha 3 or beta 3, beta 2, these things we need for the relative and absolute angles. Okay, so okay, so we now know the formula. Okay, tan beta 3. Okay, and now we have to actually simplify these above equations. Okay, there is two equations, one with psi. Okay, and okay, this is yours. Okay, this is your psi. Let it be equation number 1. This is equation number 2. From equation 1 and 2. Okay, you know what? Tan beta 3 is equal to psi by 2 plus r divided by CA by U, and tan beta 2 is equal to psi by 2 minus r divided by CA by U. Okay, so next, now substituting the values of psi, and CA by U, we take it as phi, and the degree of reaction Rx, we can find out what beta 3 and beta 2. Okay, we found out the beta 3 as 68.2 degree and beta 2 is equal to 46.98 degree. Okay, so we know for 50% reaction stage, alpha 2 is equal to beta 3 is equal to 68.2 degree and alpha 3 is equal to beta 2 is equal to 46.98 degree. Okay, okay, so next bit will be your, next is the velocity at nozzle exit. Okay, we find out the relative and the absolute flow angle alpha 2 and alpha 3. Okay, which is also equal to alpha 2 equal to beta 3 and alpha 3 equal to beta 2. All these things we just find out. Okay, beta 3 beta 2 as well as alpha 2 and alpha 3, that is your whatever your absolute and relative and absolute flow angles we already found out. Next we will find out the velocity at the nozzle exit. Okay, the exit velocity C2 we need to find out. Okay, next the static temperature. Okay, okay, static temperature as well as the mass flow also you need to find out. Okay, So let's just start the B bit. Rm is equal to 0.75. all these things we already have. You can find out the mean radius. Next is your blade speed. The actual velocity is 5 into um. So already we get 242.95 meter per second. Okay, we need actually the nozzle exit velocity. C2 equal to CA by cos alpha 2. Okay, the CA value we already now find out. That's 242.45. Phi 2 we also find out from the here. You see, we can find out phi 2 also, phi 3, everything we have. So just substitute cos of 68.2. So if solve it, you will get C2 as 652.86 meter per second. Okay, so next we find out the what? Next in the question it asked the static temperature at the and pressure at the nozzle exit. Okay, static pressure and temperature we need to find out, especially T2 and P2 they are actually asking to find out. Okay, very simple. Okay, so what is the static temperature at the nozzle exit? So T2 is equal to T02 minus C2 square divided by 2 Cp equal to 1200 minus 652.86 square 2 into 1160. So T2 equal to 1016.3 Kelvin. Okay, so next we know the nozzle efficiency. H01 minus H2 divided by H01 minus H2 isentropic. Okay, so just 1 minus T2 by T01 divided by, I just divided by H01, I take the common and both H01 cancelled from numerator and denominator. Okay, so then T2 by T01 I just write down, and in the denominator, because T2s by T01 is equal to the P2 by P01 to the power gamma minus 1 by gamma according to the isentropic relation of our temperature and pressure. That's the reason it can be converted to P2 by P01 gamma minus 1 by gamma. Okay, basically from here we need to find out by P2. Okay, so take and other things are known. So P2 by P01 to the power gamma minus 1 by gamma is equal to 1 minus T2 by T01 nozzle efficiency okay. So directly write down directly here. So if you solve P2, it will comes out to be 1.986 bar. Okay, because the unit of V01, if you see the unit of V01 given in bar, so directly we get the unit as bar. Okay, it's 4 bar. P01 is given 4 bar. If you see, the stagnation temperature and pressure, which is P01, not represents the stagnation condition. So then the last bit it's asked. Okay, so last is asked the for a nozzle efficiency of 0.96 find the mass flow. Okay, so last bit we need to find out the mass flow. Okay, we didn't okay, assuming okay, so mass flow we need to find out. Okay, mass flow is very simple. M dot is equal to rho 2 A2 into CA. Okay, apply the ideal gas equation. P2 by RT2 into A2 into CA. Substitute all these values. We have all these values and find out the M dot. Convert everything into SI units, then substitute. Okay, so this is the answer. Thank you very much for attending the section. If you are attending the recorded one also, thank you very much. This is the last lecture of the section. There may be a extra section maybe on Monday, okay, from 6 to 7 p.m. but it will be notified to you later. So yeah, so in that section maybe I can solve some of the questions from week 12 and some of the MCQs and some of the summaries. Okay, so that's the idea. So thank you very much for attending the section. Have a nice day, good night, and happy learning.